Hello, Dr. Lane. This is my reassessment for rigid body equilibrium. And so what we have here in this problem, if I can get this camera any kind of still, what we have in this problem is this metal beam, this lovely drawn metal beam, and it's being supported by two walls right here, right? By those two walls. Boom, boom. Here's this metal beam. It's got a force of 600 newtons acting on it this way at an angle of 45 degrees. It's got a dude standing on this beam, or a force of some kind, acting 200 newtons of force right there at point B. It's got 2 meters in between this wall and this force, 3 meters between this force and this force, which is pulling down, this force D, which is pulling down at 100 newtons, and then 2 meters between that force and the wall. So I kind of drew this over here to kind of clean it up a little bit because the question asks to find the horizontal and vertical components of the force of the walls on the beam, because the beam is in equilibrium. And so that would be the force of this wall pushing up AY plus the force of this wall pushing up BY plus the force of the wall pushing this way BX, because what we did when we cleaned it up is we split this 600 newtons at 45 degrees into its vertical and horizontal components there to make it easier to work with. The beam is also 0.2 meters thick, which ends up being important later on. Okay, so let's dive right into it. Since it is at equilibrium, we do know that the net force is going to be 0, because that's just the definition of being at equilibrium. And so what we're going to do first is we're going to find Bx, this right here. And we know Bx has to counter 600 cosine 45 degree newtons, because that's the only other force acting in the x direction. Since it is at equilibrium and we have to they have to be equal, then we just set up our equation. 600 cosine 45 degrees Newton minus Bx equals 0, because they both have to be 0. And when you know it, Bx is 424 newtons. So there's one part of the problem. Next, we need to find our vertical components. And what we're going to do is we're going to add up all of our vertical components, because again, AY and BY have to make the rest of the pipe be in equilibrium. So we have 100 newtons, which is this one right here, 100 newtons, and that's pulling down the 2 meters right here, plus the 600 sine 45 degrees newtons force right there, which is pulling down, which is applying the force over this space of 5 meters right there. And then 600 cosine 45 degrees newtons times 0.2 meters, because that is pulling down on the thickness of the pipe right there, minus our y component, AY, right here, times 7 meters, because it is supporting across the entire thing, and all that's got to add up to 0. And when you do that, you solve for AY, you get 319 newtons. And we're going to do a very similar process for BY. So we have 319 newtons, which is our AY in this direction, minus 600 sine 45 degrees newtons, 45 degrees Newton right there, minus 100 newtons coming from right there, minus 200 newtons coming from right there, plus BY, our missing vertical component. All that must equal 0, and BY must equal 405 newtons. So that's it. There's rigid body equilibrium in a nutshell. Nice.